All right, now we're going to revisit this idea of a z-score that you first got introduced to earlier in chapter 2. So given a random variable demonstrating a normal distribution, the individual values of the random variable can be standardized using the following equations. Um, so what we mean about being standardized is this means we're going to convert uh, datums into a unitless scale. So we're going to take datums that might have been formatted or not formatted, but may have been recorded or measured, for example, in feet or in gallons or in uh, centimeters. And we're going to take datums that were formatted in this scale, and we're going to convert it into a unitless scale, something that a number that is not in feet, a number that is not in gallons or in centimeters. This was something that we talked about in chapter 2. And when we want to convert values of x that might be in some unit, like feet and gallons, then we need to know what the mean and standard deviation is. And once we've got everything on the right side of this equation, that'll allow us to calculate the z-score, which is the value on our unitless scale. If we want to convert a z-score back into a value of x, then we use this equation to do it. And the equations for doing it with population data or sample data is pretty much the same. You'll notice here that, up here for populations, we've got the population mean here, and that is analogous to a sample mean down there for samples. Up at the top, when we're talking about converting data from a population, we need the population standard deviation. And that correlates to when we're working with a sample, we've got sample standard deviation here in the denominator. So these two equations are virtually the same. It's just the variables kind of change with the context, whether we're dealing with a population or a sample. Converting into z-scores allows us to make comparisons from two separate data sets that may have even different units or may have similar units, but are taken from two different populations or two different samples. And we want a way to be able to compare them. And so converting them both into a z-score will allow us to kind of compare them on a more on the same scale. Z-scores, are used in a lot of different places, and I just found one such example, and that was with the World Health Organization. And so I was just looking at some of their data, some of the data they had on child growth, and they had data on weight versus age. And the weight versus age data was given in z-scores. Okay, so you can see that there's that this is used, not just in an academic setting. I mean, this is used all over the world, and for just about every technical discipline you can think of. Once again, a z-score is unitless. So to kind of demonstrate how it becomes unitless, let's assume the weight of adult males in the United States is 190 pounds with a standard deviation of 10 pounds. So now one may want to know what the z-score is of the weight a specific adult male who weighs 175 pounds is. So if we're going to try and convert 175 pounds into a z-score, then this is the equation that we're going to need. So 175 pounds is the value of x that we want converted into a z-score. But in order to have everything that we need on the right side of the equation, we need the population mean and we need the population standard deviation, which is what we were given here and here. So taking the values that we were given and plugging them into the z-score equation, you can see that we substituted for x 175 pounds. For the population mean, we substituted in 190 pounds because that was given. And for the population standard deviation, we substituted 10 pounds, which is what was given. Now, typically, when you're adding and subtracting, multiplying and dividing units, you kind of follow the same algebraic rules to do so. So 175 pounds minus 190 pounds gives us a difference of negative 15 pounds in the numerator. And the denominator, we're just going to leave that alone at 10 pounds. Now, you can treat units in a very similar way as you would treat common factors. So for example, if we had the fraction 4 over 6, and we were to write 4 over 6, or 4 over 6 as 2 times 2 all over 2 times 3, well, we could cancel a 2 in the numerator with a common factor of 2 in the denominator, and that would give us 2/3. And 2/3 is equivalent to 4/6. So this idea of canceling out common factors, we can do that with units too. So we can take pounds in the numerator and cancel that with pounds in the denominator. And that gives us now a unitless number. It's going to give us a number without any units here. And now this is a z-score. So a value of x in one scale is equivalent to a z-score of negative 1.5 in the unitless z-scale. All right, now we've kind of done this mathematically, okay, but that doesn't paint a picture. So let's look at a picture of what this means. So down here across the denominator, or not, sorry, not the denominator, along the horizontal axis, this is where we have weight in pounds. And the mean is 190 pounds. So you can see here at 190, this is where the center of our normal distribution is. This is the line of symmetry. And because we're dealing with a normal distribution, it has this symmetric bell-shaped curve quality to it. And the width of this normal distribution is dictated by the standard deviation. So here, our population mean is 190. And if we take the mean and we add one standard deviation to it, that's going to be 190 plus 1 times, what was our standard deviation? 10. And 190 plus 10 is 200. And then if we take the mean plus 2 standard deviations, that's going to be 190 plus 2 times 10, which is 190 plus 20, which would give us 210. So the standard deviation is telling us something about the width of this normal distribution shape. And on a z-scale, the center of a normal distribution has a z-score of 0. One distribution away from the center is going to be a z-scale of 1. 2 standard deviations away is going to be a z-scale score of 2. And 3 standard deviations is 3, and 4, and so on. And if we go in the direction to the left, we can go 1 standard deviation below the mean. We can go 2 standard deviations below the mean, 3 standard deviations below the mean, and 4 standard deviations below the mean. So notice that we were given a value of x is equal to 175 pounds. So where is 175 pounds on our weight scale? Well, 175 pounds would have been right here. This is 175 pounds. Well, when we converted that to a z-score, what did we get? We got a value right here, which was negative 1.5. And negative 1.5 is between negative 1 and negative 2. So we converted our data from one scale into another using this z-score equation. All right, I think this is a good place to stop. Let me know if you have any questions.